This video is about acid-base titration, which is a way to use stoichiometry to figure out the concentration of an acid or base solution. So a reaction between an acid and a base, a strong acid and a strong base, is called a neutralization reaction, and the products of that reaction are always going to be a salt, an ionic compound, salt, and plus water. And the net ionic equation is always going to be the proton, H plus from the acid, plus the hydroxide from the base, makes water. All of these are going to be Arrhenius acids and Arrhenius bases. So the acids are all going to have protons, and the bases are all going to be hydroxide bases. So just for practice, we've already done lots of these when we did double replacement reactions, but just to review, do the double replacement reaction and write the product. The proton is going to change places with the cation, and it's going to make water, and then it's going to make the salt, in this case lithium chloride. Make sure that they're balanced, and then go back and check your work. Okay, a few more on the next slide. Okay, so the reason why we do titrations is it's an acid-base neutralization reaction with two aqueous solutions, and it's done in order to determine the concentration of one of the solutions, the acid or the base. We're going to use the equivalence point, which is the point where the number of protons is equal to the number of hydroxides, and we know when they are equal because we use something called an indicator, an acid-base indicator, and it is a substance that's going to change color at a very specific pH. The one that we most commonly use, the one that we are going to use in lab, is called phenolphthalein. It's the most common acid-base indicator for titrations, and it is colorless, clear and colorless in acid solution, but it turns pink when the solution is basic, when the pH goes above 7. So you know when to stop because it just is barely pink. So that tells you that you're right at the point, or close to the point, where the protons and the hydroxides are equal to each other. So in titration, because they're always the same pattern, we actually have a really handy equation that we can use, which says that the molarity of the acid times the volume of the acid times the number of protons in the acid is equal to the molarity of the base times its volume times the number of hydroxides in the base. For the volume, it can be in milliliters. They have to match. So typically volumes are milliliters, and they have to both be in milliliters. They could both be in liters, but that actually is uncommon. But you don't have to convert to liters in this case, because the two volumes have to match each other. So here's a typical titration problem. You're performing an acid-base titration to standardize an HCl solution, and standardize means that we're going to figure out the concentration of this HCl solution. And we do this by placing 50 milliliters of HCl, so we have the volume of the HCl solution, of the acid solution, into a flask with a few drops of indicator, that's to make it change color, and then we are going to titrate it, or add this concentration, 0.5 to 4 molar sodium hydroxide, put that into the burette. A burette is a device that lets us measure the volume of the base that we're adding. And its initial reading is 0.55, which means that's where the mark starts. And then after we've added all the base, in order to turn it pink, at the end point, which is the equivalence point, the burette reads 33.87 milliliters. So the concentration of the HCl solution, we can figure that out using our equation. So it's really useful in these types of problems to make a list of the variables that you know, so you know how to use them in your equation. The first one's going to be the volume of the base. We've got to do a little bit of math here. And because we're adding with a burette, it's going to be the final volume minus the initial. So 33.87 minus 0.55 means that we delivered 33.32 milliliters of sodium hydroxide base. So this is going to be the volume of the base. Molarity of the acid is what we are looking for. We have the molarity of the base, we're given that, and we're given the volume of the acid. Looking at the formulas, hydrochloric acid is monoprotic, so the number of protons in the acid is 1. Sodium hydroxide has 1 hydroxide, so that's 1. And we plug all of these into our titration equation and solve for the molarity of the acid, just using algebra. And it's going to be in M, concentration molarity. And when you solve for MA, you get 0.1016. So here's another practice, a little bit different. First step here is going to be to write a balanced equation for the reaction that you're given, which is between hydrochloric acid and sodium hydroxide. And then determine the concentration of the acid, the molarity of the acid. So before doing the math, I balanced the equation and determined that the acid has 1 proton, the base has 1 hydroxide. We know the volume of the acid. We're looking for the acid molarity. We know the volume of the base. In this time we didn't have to subtract. We were just given the volume of the base. We know the concentration of the base. Plug all those into our equation, solving for molarity of the acid, and we get 0.211 molar. Okay, one last example. In this one, we are going to make a standard acid by adding a specific amount mass of acid in order to make 150 milliliters of solution. So we're going to use our molarity equation to calculate the molarity of the acid. Then we're going to use this acid where we know the concentration to figure out a base where we don't know the concentration. So we have to do step A first. So the molar mass of KHSO4 is 136. Take the grams, divide by the molar mass to get the moles of KHSO4. Divide that by the volume in liters to get the moles per liter, which is the molarity. So this is going to be the molarity of the acid. So again, making a list of the stuff that we know. We have the molarity of the acid. That's from part A. We know the volume of the acid. We know the volume of the base. And we know that the number of protons is 1 because H has 1 proton. And then the number of hydroxides and sodium hydroxides is 1. And we're going to be solving for MB, or molarity of the base. And that calculates out to be 4.55 molar.